Okay, so how many of you have heard the term trophic level? Anybody? No, not trophic there. So we'll go back a little bit. How many of you have heard of the term food chain? Food chain. Okay, so let's make on this slide a food chain. Producer. Who has an idea of a producer? Okay, let's be more specific. Grass. Okay. You've got grass. What eats the grass? Cows. What eats cows? So this is very short. This is a very short food chain. Arrows. Anybody know what the arrows? Do you remember what the arrows represent? I think I heard it. Nope, not eats. Transfer of energy.
Credits the little lady.
What are grass called in this food chain? Producers. Come on, my P won't work there. Producers. Cows would be considered your which level consumer? First level or primary, and how you write primary is a 1 with a little degree sign. That's a primary consumer. And then humans would be your secondary consumer, which you put a number 2 with a little degree sign. I did cons just to be sure because it's not letting me write very easily. Kind of review. So trophic level, what that means, your trophic levels, is the energy level that you are at. Which one do you think is at the very first trophic level? Grass. So this is your first trophic level. And the reason why it's the first trophic level, where is it getting its energy? Sun. It's your primary trophic level, your first trophic level. I should say, I don't want to use primary because it'll confuse with primary consumers. Your first trophic level because it's obtaining energy from the sun. Your second trophic level would be then cows. And then your third trophic level would be humans. Okay, so it's trophic level is just the energy level that that organism is at. It's going to help us when we talk about your pyramids. We have 3 different pyramids. Can I go on to the pyramids? Okay, so we have 3 different pyramids. One is the pyramid of biomass. And what biomass is, it's the total mass of all organisms in a food chain. So biomass is the total mass of all the organisms in a given food chain. There is a transfer of biomass from trophic level to trophic level. Because when you eat a cow, you eat parts of the cow, right? You're eating the tush of the cow, right? The problem is we're not very efficient when we transfer that biomass to the next levels. So the food chain that you created, cows ate the grass. Do cows eat all of the grass? No. Do they eat all of the parts of the grass? Are they eating the roots of the grass? No. So they could, but not. They're not eating all of the grass, and they're not eating all parts of the grass. We eat the cows. Are we eating all of the cows that exist?
I hope not.
No. Are we eating all the parts of the cows? No, you're not eating the bones, and you're not eating, most often not the stomach and the heart. Some people do, but most often they don't. So you're not consuming all of the parts of that cow. So it's very inefficient how we have mass go through this food chain. So what an ecological pyramid is This is just one example that you came up with as a class. It shows that diminishing amount of either biomass or numbers or energy to each subsequent higher level. So normally about 10% of the energy that's available at one level is passed to the next. So only 10% goes from one level to the next. Are there more humans in this area, or is there more blades of grass? More blades of grass. So the further you go up your trophic levels or food chains, or up your pyramid, the less numbers that you have within that given level. So here's just a generic pyramid, and there I want you to know that there are 3 different ecological pyramids, okay? One of the ecological pyramids, why is that there? One is the pyramid of numbers. And we talked about how many individuals are at a given level. Like we said, there are many more individual pieces of grass, individual organisms of grass, than there are humans. A second pyramid is a pyramid of biomass. When you add up, you actually mass out all of the blades of grass, say on a farm, on a herding farm, and then you mass out the cows. Which one do you think will have more mass? Actually the blades of grass. Think about how many blades of grass you have to collect on an entire farm versus maybe how many cows? 20?
100.
No, there's not 100 cows. 20 cows. So if you actually mass out both of them, the grass would actually have more mass. And then if you mass out the number of individuals that live on that farm or that will eat those cows, the mass of the humans are going to be less than the overall mass of the cows. So that's why it's called a pyramid of biomass, because as you go to each level, only 10% will be at the next level. And the last one is the pyramid of energy. Producers, where do they get their energy? From the sun. So they get 100% of their energy from their sun. From the sun. Their own sun. From the sun. The primary consumers, they actually, again, they're not consuming all of the blades of grass. They only get 10% of the energy from the producers. The rest of it is either heat, released as heat, or used up by the plants. So it's either released as heat or used up. Now, the secondary consumers, how much will it get from the previous level? 10%. So how much would it be from your from your producers? Only 1%. And again, the rest of it goes off as heat. Oh, it has the arrow on the other side. This is your heat energy loss here. So then your secondary level, what's their percent going to be? 0.1. Then your third level, 0.01. And then your fourth level, top consumer, which I've never seen a food chain with actually 6, but in this one we have it, 0.001. So if I want to do the numbers game, if I had 1,000 blades of grass, how many primary consumers would I have? Or the mass of my primary consumers? And then my secondary consumers, and then my tertiary, my quaternary, 0.1, and then 0.01. Was that just a surge? Yeah. So this is pretty easy when you think about it. I might give you a number at a secondary consumer, and I might ask for what it is at the producer level. You should be able to do the math with it. So that's it for the energy aspect and the pyramid aspect. Now I want to talk about something that actually impacts you. It could impact you on a daily basis depending on what you consume. It's called biological magnification. It's also known as biological amplification. It's both. Amplify and magnify mean the same thing. What does an amplifier do? It makes the sound larger, right? Much bigger sound. Magnify, what does it make that image do? It makes it larger. So it means the same thing. Biological magnification and biological amplification. And what it means is it's a buildup of those pollutants at the higher trophic levels. So the impact is much larger at the higher trophic levels than it is at the lower trophic levels. What's happening, this is one example, this is a true example, and I'll tell another true example. DDT, anybody know what DDT is? What is DDT? Pesticide. Do we use it anymore? No, it's outlawed, it's banned, it's against the law. But we used to use DDT, crop dusting, have it in an airplane, go across a field, and just DDT getting down, you just open up the flow and the chemical goes onto the field to kill off the pesticides so the crops will grow. Problem is, that runoff would go in the water, go in the soil. This is an example of lake runoff, and the DDT would get into the water. ppm, do we know what ppm stands for? Parts per million. So if you look at the water, it doesn't look like it's that bad. 0.00003, I don't know if I had enough zeros there, parts per million in the water. That's not bad. But as you go up your trophic level, so your producers, the zooplankton, have 0.04 parts per million. So it's gotten, that DDT has gotten more concentrated in the zooplankton. And then your minnows are gonna eat a lot of those zooplankton, so it's gonna get even more concentrated at that next level. And then the northern pike's gonna eat even more minnows, right? So not just one minnow, but lots of those minnows, and it's gonna get more concentrated in the northern pike. And then the osprey is going to eat the northern pike, a couple of northern pikes, and it's going to get even more concentrated in the osprey, that bird. And this did happen to the American eagles, and at one point the bald eagle was actually endangered because of this DDT. What happens to it is that it can soft shells. Eagles won't survive when they're born. They're have some chemical damage to them, so they won't survive. They can't reproduce, and we know evolution. If you can't reproduce, then your species won't survive. So we've outlawed it. Now we have a thriving bald eagle population in the United States, and we don't have that problem anymore. Anybody know what a current biological magnification problem is in the United States? Humans should not eat a ton of tuna. Why? What's the chemical in them? Anybody know? Not lead. Close. Mercury poisoning. Have we heard of it? Mercury poisoning? You're told, especially pregnant women are told to not eat a lot of tuna when they're pregnant. And humans are told that as well. You shouldn't have consumed tuna every single day because we are the top of the food chain. So it's going to be so much more concentrated in our bodies. It makes us sick and it can kill us depending on how much you eat of it. Plus, for those pregnant females, it can actually go through the bloodstream and into the fetus. And so, can you eat tuna? Yes, I had tuna last week. It's sushi. It's fine. But if you have it once a week, once a month, that's not going to be a problem. If you have it 3 meals a day, every day of your life, you're going to get sick. That's why these individuals, that's what they eat. Their food that they consume is the fish. That's what they eat for every single meal, and that's why they were more impacted than humans. Yes?
Isn't that the case with every fish now?
There are some fish that have higher mercury counts than others based on their gills and how it diffuses into the body. Tuna is worse than salmon, and whitefish isn't as bad. So I think the hardier fishes are actually worse for you because more of it goes, it's a higher concentrated value. So back to this. It was one of the Kahoot questions on there. So I want to make sure that you understand the actual scientific definitions of these. A population is a group of the same species, individuals of the same species living in a given area. That's what population is. Community is all the populations that live in that area. So we use the term Stevenson community, don't we? What are we referring to when we say Stevenson community? The what? People, right? All the students or the teachers and the students. Would that be, in our terms, is that the correct definition to use, Stevenson community?
No.
What should you use instead? Population, the Stevenson population. If, however, you guys want to talk about the grass outside, the cockroaches that live in the building, the geese, the mice, and the rats that live in the building, and all the students, then you can say Stevenson community. Okay, so you want to make sure community is many populations, all the populations that live in a given area. And community is just biotic. Okay, community, when you're talking about community, it's really talking about just the biotic factors. Now when you bring in talking about the influences of both the biotic and abiotic, that's when you talk about your ecosystem. So remember, the people, the geese, the grass, the plants, the cockroaches, the mice, the rats, and if you talk about the rocks and the soil and the sky and the water, you're abiotic, that's when you're talking about the Stevenson ecosystem. Okay? Habitat, not crib, for whoever chose that answer, is the environment in which that species lives. And that's that given species lives. The niche, and we're going to have an example in a couple of slides, I think, is the role where you play in that ecosystem, in that habitat, I should say. Here it's a little different. You can be in the athletic niche or the fine arts niche in actual organisms. It's going to be more of the location. On the lower level of the tree versus the canopy of the tree, those are different niches that you live in. Population growth. Populations grow and are affected by limiting factors. What do you think limiting factors means?
Weather.
Weather can be a limiting factor, yes. Yep. Did everyone hear Emily? Emily, will you say what limiting factor is again?
It's something that prevents the population from changing.
Growing would be, yeah. Growth depends on the rate of reproduction. This kind of makes sense, right? If you don't reproduce, are you going to grow? No. If you reproduce, you're going to grow. There are certain countries that had problems. They were overpopulated. What does this mean? Allowance options for your parents? Well, what's a country out there that limited the amount of individuals they could have? China, right? Was Korea one? North Korea was one? And so in China, I know for sure for China, you could have one child. Right? It was overpopulated. It was running short on resources. And so there's this idea of there are some countries, more communist countries, that will have that you can have one, you have an allowance for one. If you have another child, several things could happen. Way long ago, they could exile that child, tax you on that child, take money away from you, which is kind of similar to tax. And so that was happening. And still happens today, some of it. If nothing limits your growth, you have no limiting factors. The kind of growth curve you have is called an exponential growth. And the reason why they call it J-shaped is that's what the growth curve looks like. It looks like the letter J. So exponential growth curve is talking about every single generation, next generation, will actually be a multiple of the previous. It continues and continues to grow in numbers. Human population really is the only population right now that will have exponential growth curve. You won't really see it in any other type of organism. And no matter what the rate of growth is, the shape of the curve is always the same. It always continues to grow in that exponential form. Different factors in growth. If you think about it, it makes sense. Birth rate, how many are born, your natality rate. Immigration, how many move into a specific area. Death rate, how many die, mortality. Emigrate, how many move out. So depending on these rates will depend on your growth rate. If birth rate and immigration are far higher than death rate and emigration, your growth curve is gonna increase. If death rate and emigration are higher than birth rate and immigration, your growth rate is gonna decrease.
Is emigration the opposite?
Yes, it means to leave, to exit. I'm not going to go into the bottom one. You're actually going to read about it, I think, tonight or tomorrow, sometime this week. It's talking about how we can predict the future of how big the population will grow in both us and other organisms. Your limiting factors, like Emily said, this is what stops your growth in that population. So it prevents exponential growth from taking place. It's a factor that stops your growth from taking place. Competition will occur. The reason why competition will occur is because a given area has a carrying capacity. That's the number of individuals that will survive in a given area, that's able to live and survive in a given area. So an example for us, we have 24 individuals in this room plus me, so 25, right? What if 2 new students transferred into this room? We locked the door. We only supposed to have 25, so 25 meals were delivered 3 times a day for however long. What's going to happen now that we have 27 individuals in the room? You're going to fight. You're going to compete for the food. Would you share your food? Think about it in terms of evolution, not in terms of being a human. Are you going to share your food? No. You're going to have fights. I might put 4 meals at each table and 1 at the teacher table because I get my own meal. 4 meals, and so what you might do is you might fight each other. Whoever has those extra individuals, you're going to fight and you might kill. Even though you have enough food, you're still going to fight to make sure that you get that food. So your population will actually dip down under 25 because you'll probably kill more people than just 25. But then you guys are going to reproduce. So what's going to happen to your population? It's going to go back up. And then it'll go down, and it'll go back up, and it kind of stays like this S-shaped curve. It shows you don't need to know your constants, that equation you don't need to know. You just need to know the shape of the curve. So your S-shaped curve is one that has a carrying capacity and one that has limiting factors. And what's going to happen is it might go up, it might go down, it might go up, and it might go down. But it's this kind of sideways S here, if you see it, if you make it sideways, it's going to hover around your carrying capacity. So what are some examples of limiting factors? You have 2 types of limiting factors. You have what's called a density-dependent factor and a density-independent factor. Density-dependent, I hate using the same words, but it depends on the density of that area. So in this room right now, this nice big room, the density of this room is 24, because we have 1 missing, 24 individuals. Disease is an example. Sorry, Cameron, I'm giving you strep throat. Cameron has strep throat. Do you think Emily, Adam are going to get strep throat? Is Jamie going to get strep throat?
It's possible.
Yes, but it might not be likely. Who's more likely, over there or over here? Over there. It depends. That's a great word. Now I make a wall right between Adam's table and Amanda's table all the way. Force all of you to go and sit in the front. Who's going to get sick? All of you. It depends on how dense that area is. It's much more dense if I put 24 of you in the front of the room versus spreading you out. And so that's the example of density dependent. So examples of them: disease, competition, predator-prey. Those are going to be density dependent. Your density independent, it doesn't matter how dense it is. Your natural disasters. Do you think whoever is responsible for the weather, we're not going to go into discussion about that, but do you think that back in, October, when the tornado hit Washington, Illinois, did they say, ooh, that's a really dense population, I'm going to have that tornado hit right there? No, it's whatever that climate change, the weather patterns, it's going to happen regardless of how dense that area is. Seasons happen regardless of how dense it is. Human intervention, we're very selfish. We don't care how dense a population is. We're going to go hunting, and that's why now they have licenses and hunting area. I think it's from November to, is it in, July or something like that. You can't hunt all year round in Wisconsin because they need to make sure that the population will remain steady. If we had our choice, some hunters would hunt all year round and you don't care about how dense it is. Malthus, you read about with evolution, he predicted, and we'll see, we're not there yet, that there's going to be a point where we're going to suffer. And there's going to be lots of disease, and we will reach our limiting factor, our carrying capacity. Have humans yet? All humans. You can't think of just a certain area. Yes, third world countries might have more disease, but you got to think about the entire human population because we're one population. We're one species. Is there a limit to our population? I don't know. We haven't reached it. The answer is we have not reached it yet. Oh no, one more minute? Not even? Shoot. This is going to be online. I'm going to make sure that I get through it right now. So you can finish it tonight. I'll put it online. And Web of Life is a good movie that we're going to see on Friday that really talks about interactions. But I promise you that it will be online.